Okay, welcome to the new video. Today we're going to talk about the general axiom over V-preference. So this is the basic theorem in V-preference analysis. So in order to start, let's assume that we have some data set. Right. A data set, and our data set consists of two things. We have prices and we have quantities, right, for some observations T and big T. Which means so we have a vector of prices. So P1 is a vector of prices, P11 until P1n. P2 is also a vector of prices, P21 until P2n, and so on. And also Q is a vector of quantities, Q11 to Q1n, and so on. Right, so here n is the number of goods. And T is the set of observations. Okay, so we say that we define a binary relation on this set T in the following way. So we say that an observation T is with U preferred to V, and you write it like this. If the following is true. So if you sum from I from 1 to n of PTI QTI, then this should be greater or equal to the sum of 1 to n of PTI QVI. Okay, so this is the relation, and if you write this in vector notation, you have that the transpose of PT times QT should be greater or equal to the transpose of PT times the vector QV. Okay, so this is the basic review preference relation. So this is the normal review preference relation. You also have a strict review preference relation. And this is the same, except that you don't have a weak inequality, but you have a strict inequality. Now, given these two relations R and P, you can define GARP. So GARP says the following. If you have a number of observations, let's say that T is review preferred to V and V is review preferred to S, and so on, until finally this is review preferred to, let's say, R, well, then you should have that R cannot be strictly review preferred to T, right? So this cannot happen. All right, so basically this is the definition of GARP. And as you might recognize, this is nothing else than saying that T is review preferred to R in an indirect way. So this is the R star is here the transitive closure of R, right? And we know how to compute the transitive closure. We will use Warshaw's algorithm to do this. So this is the theory behind GARP. It's not very difficult. So what are we going to do? We're going to need to define R and P. We need to compute R star, and we need to check if TR star V, then you don't have that V is strictly should be strict review preference relation, strictly review preferred to T. Okay, so these are basically the three steps. So given this, let's start with the program. So let me go back to Julia, and I already have the function Warshall that we defined previously. I only made a very small adjustment. So in the previous program, what I had here when I introduced the path, I had it like this, right? So this is basically a matrix. There's a problem in Julia. Julia sees this as a two-dimensional object. So if you want to have a one-dimensional object, what you should do is you should define it as a vector. So you should put a comma into this. And this is better because the append is not really going to work well when you have two-dimensional things, but it's going to work excellent or very well if you have a vector, right? Right, so we have a function, a new function, which we are going to call GARP. It's going to have as inputs prices and quantities. All right, so what are the prices? The prices are going to be, we're going to store them in the matrix. All right, so basically this is an array. The array is going to contain floats or integers, I don't know. So anyway, it's going to be something less than a real. It's going to have two dimensions. The Q is going to be of the same type. Alright, so this is going to be my function. Let me first compile Warshall to be sure that I have this one. Then I have GARP. Okay. Small typo. Okay, so let me just define P as being a random vector of size 2 times 3 and Q to be a random vector of size 2 times 3, just to be sure that this function, note that I don't have any typos. So I also need to compile P. Alright, so it takes up P and Q. So what do we need? Well, let's first check that P and Q are of the same size. So I'm going to, P is a matrix, and the rows are going to be the observations, and the columns are going to be the goods, right? So the size of P, the rows are the n observations and the n goods, and you have the same for Q. The observations for Q and you would like to make sure that P and Q are of the same size, right? So what do we need? We need that the number of rows of P is equal to the number of rows of Q, and we also need that number of goods in the matrix P is equal to the number of goods in the matrix Q. And if this is not true, then we're going to say please make sure that P and Q are of the same size. Alright, in order to see that this indeed works, let's take P to be 2 by 2. Alright, so we have an assertion error. Please make sure that P and Q are of the same size. Okay, so this seems to work. So first of all, what do we need? Let's check what we need. We need these kind of quantities that are here, right? PT times QT, and we need PT times QV. Alright, so what are these? These are dot products or vector products, right? So let's first define a function vector product. It's going to take two vectors. And what it's going to do is going to return the sum of a vector of xi times yi for I n 1 length x, right? So this is a very quick function that's going to give us the vector products. So let's compute PTQV, and we're going to store this in the matrix. So on row T and column V, we're going to have PTQV. So what do we have? We have the vector product of PT, right? Row T times QT for Tn1 and ops. Okay, so let's first return PQ to see that this is indeed working. Of course, I need to define them by the same size. So let's first have two goods, right? So this is easier to compute. Right. So let's see here how these matrices look like. So let's, for example, compute first element 2.60. So 2.60, let me compute below, should be 0.0637 times 0.640941 plus 0.680747 times 0.321358. And we get as a result 2.59, which is close to, which is exactly, almost exactly this one, right? So I'm not so good as a computer, but this seems to be quite okay. So we have these things. All right. So what is next? Next, we need to derive or define the relations R and P. So we're going to store R in a Boolean matrix. So what this is going to be, we're going to check if PQTT, right, PT times QT is greater, or so GE tap, this is going to be the greater or equal sign, PK times TV. If this is true, then we're going to get a true for R, right? And otherwise we're going hopefully get a false. If this is true, then we're going to say true, else we're going to say false. And we're going to do this for Tn1 nops and Vn1 nops. Alright, so let's return R and see if this works. So we have GARP. So this doesn't seem to work. Why not? Oh yeah, so I have to define PQ as a T by V matrix, right? So you have the end product of this and this. PT times QV at row T and column V. Alright, so now we have a 2 by 2 matrix, right? Now we can define R, and now it should be okay, I guess. Right, get a 2 by 2 Boolean matrix. So the first one is Ruby preferred to the first one, of course, right? Because it's on the diagonal here also, and one is Ruby preferred to 2. Alright, so let's check that this is correct. Let's also return the matrix. So we have that 2.5 is greater or equal to 2.5. This is lower than this, so this is false. This one is greater or equal to this one, so this is true. And this one is greater or equal to this one, so this is true, right? Let's take it 3 by 3, such that you have a little bit more comparisons. Alright, so 0.61 is greater than 0.57, so this is true, and so on. This is false because 0.73 is smaller than 0.97, and so on and so on. Okay, so this seems to work. We also need to define the strict review preference relation. This is basically the same, except that now we have the strict version. Okay. So what do we need to do? We need to compute the transitive closure of R, which is easy to do because it's going to be by Warshaw's algorithm, and then check that if T is indirectly repreferred to V, then we don't have the reverse for P. Okay, easy enough. That's the indirect review preference relation is equal to be Warsaw R, and remember Warsaw also gives you the path, so let's also store this one. We never know that we might be interested why we have a GARP violation. And then for T and we check that if T is indirectly V preferred to V, and the reverse is true for V over T, then we return false, right? So GARP is not satisfied, and else we are going to return true. Okay, so this seems good. Partial is not defined because it doesn't have a C in the name. So it's true, right? So this satisfies GARP. So the problem here is a little bit that let me take two other ones. This is also true. Let me, for example, get a 4x3 and a 4x3. Maybe this will give a violation. So this is false, right? So you should have a review preference cycle, but you have absolutely no idea how this review preference cycle looks like. So what can we, for example, do? Well, we know that there's a review preference violation here, right? From T to V and from V to T. So what we could do is we could also return a path. Let's compile this. All right, so let's not return the entire path, but also only the path from T to V. So why is this not returning the path from T to V? All right, here it is, 1, 4. Right, so apparently there's 1 is review preferred to 4, and 4 is strictly review preferred to 1. Okay, so again, there's not really how to check this. Well, we can easily check this using this PQ matrix, right? So let's also return this PQ matrix in order to see that this is indeed what's going to happen in this example. So 1 should be review preferred to 4, right? 0.72 is bigger than 0.51, which is true. And then 4 should be strictly review preferred to 1. 0.54 here is strictly bigger than 0.49, right? So this is our review preference cycle. So GARP is violated. We could have cycles of longer length. Let's see, so this satisfies GARP, great. This also satisfies GARP, again, great. So here, again, we have a cycle of length 2. I would like to get a cycle of a bit longer length. Maybe if I increase the number of goods, this is going to help me. No. I can continue doing this for a very long time. Here we have a cycle of length 3. So 2 is review preferred to 6, because 1.6 is bigger than 1.41, right? 6 is review preferred to 4, and 4 is review preferred to 2, right? And you can check this using these numbers. Okay, so this will give you at least one review preference cycle. So this is nice. The problem is a little bit that if you have a violation, you return 3 things. If you don't have violation, you only return 1 thing. So we should probably return something that's the same for everybody, right? So in case true and in case false. So let's make a structural element, right? And we're going to call it an RP test. So if you run an RP test, we're going to give back an object that's an object of type RP test. So what are we going to return? We're going to give the answer to the test, which is going to be a Boolean true or false. All right, and we're also going, you might want to return the name of the test. I'm going to be the string, and then let's just gather everything else in something like comments, and this could be anything. All right, so we don't put any restrictions on this thing. So in some cases we don't want to return comments, so in this case we might define also the RP test when it only has a name and a string. Write it like this. This is, and then we're going to return the empty string, right? Or no comments. Let's call this 0, right? Okay. So RP test. So what are we going to do? We're going to return an RP test object that's going to be false. It's a GARP test, right? We call it the GARP test, and then we're going to put, let's put PQ first and then path TV second, and let's make this into a cycle, right? So we're going to append, going to take party V, and V is also going to T, so we're going to append the last one, right? So we basically are returning a cycle, a review preference cycle. And if the test is true, right, then it's true, and we're still testing for GARP. So this is going to call the smaller function, so it will pass automatically the 0 as a comment. Okay, so let's do this. So if you run GARP now, you get an object that's an RP test. The answer is false. We run the GARP test, and you have some comments. So this is the income matrix which you have here, and then the cycle which goes from 2 to 6, from 6 to 4, and from 4 back to 2. Right. So this is the review preference cycle that you have. So we have also some additional information. So why the test was satisfied. All right. So if you just want to have the outcome of the test, you can do a GARP PQ time answer, right? And this will only give you false or true. So you don't have to get the entire object out of this. You can just do some kind of object orienting programming to get the answer from the test. All right, so this was the GARP test. Looks good. Hopefully it works good. Right, that's it.